Then how to do the size distribution of these different particulate matter particles. So here you can see in this particular diagram, the four different sizes are defined here. The very first size here you can see is the coarse mode. So what is the coarse mode? The coarse mode particles are having size range of 1000 nanometer to 10,000 nanometer. And all these particles in this particular range is called as the what coarse type of particulate matter. So all the mineral dust, volcanic ash, sea salt, plant debris, pollen, bacteria, spores are in this particular range, in the coarser range. Then we have the accumulation range or accumulation mode, which is having size range of 100 nanometer to 1000 nanometer, and that is having the aqueous haze smoke particles. Then we have 10 to 100 nanometer particle which is called as the Atkin mode or Atkin nuclei. So here soot particles you can find out. And then we have the nanoparticles range in the range of 1 to 10 nanometer aerodynamic diameter. And this is in the nucleation mode or nucleation size, you can say. So these are the four categories of the sizes of particulate matter. One, two, three, and four, and their particular examples are provided here in the above slide. The name of these different types and their respective sizes. That's all you have to remember. That is the most important thing that you have to remember in this particular slide. So I hope it is clear to you. So here this delta T is equals to lambda multiplied by delta F. Delta F is the change in the radiative forcing value. Lambda here is the climate sensitivity parameter that is fixed. This is a constant 0.56 Kelvin per watt per meter square. If you multiply the delta F value with this particular constant, you can see how much there would be temperature change. This is the formula that you can use if delta F value is provided to you and if you have to calculate the delta T value. And so here, this is the change in radiative forcing. So delta F is equals to 6.1 multiplied by ln natural log C divided by C naught. So delta F is the change in the radiative forcing here. The C is the current CO2 level. So suppose how to calculate this delta F value. So this delta F value is mainly dependent on the carbon dioxide amount present in the atmosphere. Higher would be the carbon dioxide concentration, more would be the radiative forcing. Lower would be the carbon dioxide concentration, lower would be the radiative forcing, because the highest contributor of the radiative forcing in the atmosphere is the carbon dioxide that we all know. So suppose if you want to see what would be the change in radiative forcing amount by the increased amount of CO2, so that you can see by this particular formula. Then if you put this delta F value in the previous formula, you can see how much would be the temperature change. So the same thing is used here. That is delta F is equals to 6.1 value constant multiplied by natural log C divided by C naught. So the current CO2 level would be your C, and the C naught is the reference CO2 level. What is the reference CO2 level? Reference CO2 level is nothing but it is just the value of the CO2 or amount of the CO2 present in the atmosphere at pre-industrial era during the 1800 times or during the 1850 or before 1900 times. So on that time, the CO2 level on the atmosphere was 280 ppm. So the same thing is written here. So in the value of C naught also, the value of that is also fixed that you have to put is 280 ppm. So I hope this formula and the previous formula both are clear to you. There is a questions multiple times asked in the examination, so that we will cover right now. Calculate change in the radiative forcing and temperature. It means delta F and delta T. Both you have to calculate when the CO2 amount is doubled from the pre-industrial era. So however, whatever was the CO2 amount in the pre-industrial era, now that CO2 amount is doubled. So you have to calculate first the delta F value, then you have to calculate the delta T value. So here let's see the solution. So here we know that the first we have to calculate the delta F value. Delta F value would be 6.1 multiplied by natural log C divided by C naught. So whatever the pre-industrial era value means, this would be 2 C naught divided by C naught. It means the present concentration of CO2 is how much? That is double to the pre-industrial era, that is 2 multiplied by C naught. So this is cancelled now, this is cancelled now, this would be ln2. So this would be 6.1 multiplied by natural log of 2. So natural log of 2 can be written as 2.303 multiplied by log 2. So I have already told you the formula. The ln x is equals to 2.303 multiplied by log x. The same formula I am using here. So this is now 6.1 multiplied by 2.303. This would be almost around how much? Let's see. Multiplied by 0.3010. So I hope till now everything is clear to you. So this would be around 13, 14. 14 if I take for the approximation value, this is multiplied by 0.3, and this would be now 42, or you can say 4.2. So 4.2 or approximation, the 4.3 around 4.2, 4.3 between value you will get here. This is what you are getting. This is the delta F or radiative forcing watt per meter square. Now you have to calculate the delta T. Delta T is equals to, we have seen that is lambda multiplied by delta F. Lambda value is fixed 0.56, and this multiplied by delta F that you have calculated, that is around 4.2. So you can see that this would be around how much? Approximately 2.5. And this value you will get in Kelvin. So degree Celsius or Kelvin, both you can say. No problem at all, because in the relationship of degree Celsius and Kelvin, the difference would be same. So here you can see that by doubling the CO2 amount in the atmosphere from the pre-industry level, that from the 280 ppm level, right now we have around 419 ppm of CO2. So doubling from that, it means from the 280 you will go to the how much? 3356, 560 ppm. So whenever we reach to the 560 ppm, the temperature of Earth would be 2.5 degree Kelvin more as compared to the pre-industrial era. That is what the meaning of this particular calculation. So I hope now this particular calculation is clear to you. And by providing any value to you, you can calculate the values here easily without any problem. So here first you have to calculate the delta F value. Once you get the delta F value, multiply with the lambda. Lambda is 0.56, a constant here. So 0.56 multiplied to the delta F is, the value you will get is the change in the temperature on the same change in the carbon dioxide concentration. So I hope it is clear to you right now. And I'm moving ahead. This is the chart of the radiative forcing. You can see that the current radiative forcing of the Earth is around 3.2 watt per meter square. And out of this 3.2 watt per meter square, 2.1 watt per meter square is directly contributed by the CO2. So remaining 1.1 watt per meter square is contributed by all other global warming gases present in the atmosphere. So here you can see in this particular chart how the different things are contributing to the radiative forcing. So the red line is showing that the particular thing is contributing towards the positive radiative forcing or global warming. This is the middle line you can see. And the blue side is showing that that particular contributor is reacting, or it is giving, or it is providing the global cooling effect. So here you can see carbon dioxide having almost highest among all amount of the positive radiative forcing. Then after that, methane is the main contributor. Then we have nitrous oxide, some amount of halogenated gases. Then there is a nitrogen oxide. Nitrogen oxide is contributing in global dimming, you can see. So this is providing the aerosol particles, and the secondary aerosol particles contributing towards the which side? Towards the global cooling side. Then we have the volatile organic compounds, VOCs, also contributing to the global warming. sulfur dioxide also contributing to the global cooling, because we have seen that the sulfur main effect is the sulfur dioxide main effect is global cooling, not global warming. And organic carbon is cooling down the atmosphere, while the black carbon, because the black color is there, so it will absorb more sun radiation and it will contribute towards the global warming side. Then ammonia we have here. Ammonia is also create the NH4 particles, which is also secondary aerosol and causes the global cooling. Then land use reflectance and the irrigation, that is also reducing the temperature of Earth, contributing to the cooling side. And aviation contrails means the pollution which is formed by the aviation industry, by the aeroplanes. So that is under this global warming category. So this is what the current scenario of radiative forcing in our Earth system. So here you can see this is the human activity causing the global warming. This is human activity causing the global cooling. And this is the total combined effect or total human influence on the radiative forcing that you can see here. And this one is the solar and volcanic drivers, very negligible effect. And the same case you can see in the internal variability of the things, very less effect. So only the anthropogenic activities or human activities contributing to the change in radiative forcing. So I hope this particular chart is clear to you right now.